So the third talk of today's evening session is by Professor Dokyun Lee, and his talk is titled InnoVAE, which is Generative AI for Understanding Patents and Innovation. Professor Dokyun Lee is an assistant professor of business analytics at the Carnegie Mellon University. And Professor Dokyun, he studies the application, development, and impact of AI in e-commerce and the digital economy. Two of his current streams of research are developing and applying interpretable machine learning and natural language processing algorithms in different business settings, and also the economics of unstructured data. Example application domains include content engineering, technological innovation, social media advertising, recommender systems, and persuasion. His research has won many Best Paper Awards as well as research grants from several organizations such as Adobe, Bosch Institute, Marketing Science Institute, McKinsey & Co., NVIDIA, Net Institute, and NSF. So it's a great pleasure to have Professor Dokyun Lee present his work on InnoVAE, and we are all eagerly awaiting. Over to you, Dokyun.
Thank you so much for having me. Very glad to be here. Yeah, very honored to be here. There are a lot of participants. So I'd like to present InnoVAE, Generative AI for Understanding Patents and Innovation. This is a joint work with Josh Chang and Sunny Tanbei. So one of the most discussed technological innovation and general purpose technology is AI. And AI has been presented as a technology to create technology or invention of method of invention. And we have seen successful applications of AI in creative tasks such as composing music, drawing paintings, and searching novel molecules even. And these tasks were commonly categorized as work of creativity, traditionally believed to require human intelligence. But slowly, AI is beginning to encroach on creative and inventive spaces. Of course, we're not automating these tasks anytime soon. In fact, many fundamental questions related to the topic of AI for innovation and creative tasks remain unsettled. For example, even the definition of creativity is a heatedly debated topic. But AI to augment the invention of new technology or to aid creative tasks is ripe for serious discussion. So you can see that there has been a rising number of companies developing AI tools to augment scientific discovery. For example, Schrödinger and Atomize are some example companies that aid drug discovery by finding candidate molecules and compounds. So they have physics engine, for example, Schrödinger has a physics engine model of chemistry and molecules, and often utilize predictive and generative models to run simulations and to identify likely candidates for effective drugs, compounds for things like batteries. So we also see a rise in number of papers published in top journals in the application of AI, specifically deep learning and generative models, to aid scientific discovery and progress. Despite the success in AI in these creative endeavors, especially generating faces is just really good these days, right? The capacity of AI to introduce new ideas or to innovate actually remains a subject of inquiry and debate. So this is a complex question that scholars have only begun to explore, and even the most basic definition of algorithmic creativity and innovation remain unsettled. So unsolved argument remains where one side claims the machines neither cannot be creative nor identify creativity, and that should be left to humans as it requires intention. That's another whole sort of philosophy there. Another side arguing that no, we can start somewhere and provide some frameworks and definitions, and that is the field of computational creativity, which has been thriving recently with the advances of neural network generative models like GANs and VAEs. So philosophy of creativity literature argues that before an intelligent agent or algorithm can generate a creative artifact, it must be able to distinguish what is creative or not. An ability that typically requires a proper representation and understanding of the data. In other words, to create innovation, the AI needs to first recognize innovation. And to recognize innovation, the AI needs to first properly represent innovation, right? So these are all subtasks. So in this research, we're carving out a very small aspect of this big themed question and investigate how we can represent an innovation. So first we prototype what we call Innovate to estimate disentangle representation of patents using both structured and unstructured data. This disentangle representation, a bit of background here is we generate this representation via generative deep learning model. What it is it maps any real world objects, multimodal objects like patents or anything really, into a low dimensional vector space where each dimensions are extracted in such a way that A, they're statistically more independent, so they are semantically more orthogonal, and B, movements within this space are rendered meaningful and more understandable. So consider like a bit of background in what I mean by disentangle representation learning. I know a lot of people here are maybe familiar with it, but consider all the cylinders that was ever created and that will ever be created. You can represent all of these cylinders in just 2 dimensions, radius and height, right? Disentangle representation learning or disentangle representation learning does an algorithm that is for disentangle representation learning. It looks at all the population of cylinders in the world and then extracts out, you only need 2 dimensions, radius and height. And that's basically what disentangle representation means. Finding sort of fundamental independent factors that you can use to generate an object. So ideally, patent will now reside in an interpretable vector space if I were to apply this disentangle representation learning. And for example, if we use computing patents, it may reside in dimensions like security, human-computer interaction, and so on and so forth. The basic bottom line here is if the disentangle representation learning works, and if we apply it to patents, now these patents will be embedded in a vector space where the axes are sort of canonical factors of innovation, depending on the groups of patents that we look at. A bit of visualization here. So you can see that in this case, we just have 3 factors. Axes are encouraged to be independent and interpretable, and patent will be embedded into a point in this vector space. Directions in this, what we call innovation space, are rendered meaningful. So movement in one direction means that you have more of that factor, or you're more exceptional in that factor, whatever that factor that may be. So for example, patent B here has increased factors 2 and 3 compared to patent A. Factors should be distinct, and this approach is not possible in any other approaches like the usual TF-IDF, LDA approaches, or any other way of even doing some embedding based on some like word to vec or dot to vec and things like that. More visualization. What we can do now is, based on this patents that are embedded in the innovation space, we can actually represent firms as a centroid of all the patents owned by the company, right? Of course, this makes an assumption, but this enables us to do lots of exploration on the economic side. So a bit more, why do we need disentangle representation? Good disentangle representation enables control generation. So we can generate patents on the fly with the trained model. It also enables data-driven unsupervised exploration at the patent level, meaning we can identify creativity level or sort of innovativeness and novelty of a patent without any labels. We can also explore innovation factors that comprise the innovation space, extract factors of innovation that comprise a particular set of patent group. We can also characterize firms to have their patents and the ability to, we gain ability to situate firms in innovation space for comparison. And I'll show you some examples of this. A different way of saying this is we can ask and explore, what can you get if you combine patent A and B? Or you can even do how innovative or unusual is a patent. For example, I populate a patent with respect to specific technological factors that's going to be extracted out, like user interface and things like that. You can also ask what company excels in technological factor X. And if you can answer this question, there are a lot of different sort of applications down the road, acquisition, patent protection, things like that. You can also even ask, if I'm firm A, what innovation do I need to boost up to be more like firm B, right? And so on and more. So empirical strategy, here's an overview of the strategy. We customized semi-supervised beta variational autoencoder, and we prototyped it in 240K patents. Usually, we chose a group of patents that are computing patents and prototyped it. Then we also operationalized creativity of patent via using philosophy of creativity and geometric interpretation in this innovation space. And we also, just to see the value of these innovation space, we compare and we correlated patent creativity that we operationalized with existing economic and technological impact of patents from the patent literature. All of these are exploratory and correlational. We also then visualize, explore at the patent level, firm level, and innovation factor level patterns that we can extract, and some interesting patterns. Some result highlights. Innovate does pass sanity check. We do a bunch of checks. For example, we see that interpretable factors of technological innovations are extracted, things like security, human-computer interaction, and so on and so forth. And latent patent encodings that we uncover or we embed in this innovation space does have a signal. It improves downstream prediction tasks compared to other existing models. Reconstruction of patent abstract also look okay. But bottom line, that's just like, does the model, is it sensible? Does it pass sanity check? But the more interesting thing is, Innovate does provide a signal about the value of patents or its exceptionality, overall creativity, as well as we can see, we can do a bunch of things, which I'll show. I think I got a bunch of questions. Whether we access patent confirmed with multiple factors. Okay, I'll skip that. I didn't understand. Okay. So a bit before, I go into the model, this overview of what is generative model and why generative model is required. So our model is a generative one, which is different from discriminative approach that, that models probability of label Y given some X. Our model is generative, where we're just actually modeling the joint distribution of X and Y if we have Y, or just the data generating distribution P of X, right? So generative model can be discriminative. This is used to create real world instances, and it's a modeling of a real world object, in our case, patents. Remember, our goal here is to categorize technological innovation with respect to their creativity level. But since there's no existing label Y to directly achieve that goal, a good way to understand the innovation is by actually simulating innovation via generative model. By using a particular generative model that provides insight into building blocks of patents. We can let data-driven approach tell us something about the innovation. Right? So of course, we're not saying this is the right model. Of course, all models are wrong. It's just one prototype that lets us sort of explore more into the factors of innovation. A trivially feasible approach is to gather human labels and make black box prediction model the Y variable might be some sort of innovativeness, creativity, and things like that. But this is nothing theoretically interesting. It can scale. It doesn't dissect the patent concept space or inform us anything about the composition of what makes a innovation creative. So as Richard Feynman alluded, to understand innovation, we have to start by prototyping a generative model. Right? So we do so by disentangle generative model, as I alluded to before, and we decompose patent into independent and interpretable canonical factors. Our model so we first need to represent each patent as an n-dimensional vector, and we choose autoencoder for this job. because the structure of disentangled VAEs is very apt and controllable. The method has been added. It also has an added benefit of making things more interpretable, understandable, which is useful for managerial implications. So we assume that data generating processes is as follows. So humanity, or the inventor, samples a random vector Z as an innovation embedding. This embodies a patent. And humanity, or the inventor, then implements the concept from this idea space into a real world instance X. And this is what we see, what we observe, that's the patent. And a bit of background in the variation order encoder. All it is any sort of multi-view or multimodal object goes in, and then it finds a latent embedding. Then it can also then generate from this latent embedding the original patents here, right? So we have encoder and decoder. So we implement our VAE with 2 LSTM network with customized loss function. So first part is the reconstruction loss. This makes sure that the latent embedding space representation does carry good signal. And the second part is basically the disentanglement inducing term, which means it makes the axes that, the innovation space axes a bit more independent. So Kullback-Leibler divergence term that pushes the encoded representation or posterior towards prior P of Z here, which is assumed to be isotropic multivariate Gaussian. And it induces further disentanglement. This one right here, just basically make sure that for the structured data that we already know for the patents, it retains that characteristic, right? Think of this approach as a more sophisticated nonlinear factor analysis, sort of. Differences and benefits are that it's multimodal. It can incorporate both structured and unstructured data natively. It can do control generation of any multimodal entity. We can also add a supervision with known key variables. And lastly, the disentangle implementation that I've been talking about. So don't have much time left, so I will go into the results. So we used the data sets, US patent file in the G06 category. It's patents on computing systems, about 240,000 patents from 1980 to 2010. It includes data patents like PageRank, multi-point touch by Apple, and so on and so forth. And these are some X variable that we have used. We used patent abstract for prototyping. We use things like word count, number of patent claims, backward patent citation, and so on and so forth. So I'm going to skip the model validity check for the sake of time. I only have, I think, 10 minutes left. So we do some sort of just overview is that reconstructed text looks, all right. It does have grammatical problems with this sentence complexity comparison and token similarity. We do the latent embedding vectors does have a signal that predicts some Y variable outcome better than other models. And these are some of the extracted factors. So this is the actual axis description. So some dimensions are meaningless. So they seem to have some sort of grammatical function or things like that. But we do extract out very specific and interpretable factors. So for example, human-computer interaction described by interface, control, mouse, and so on and so forth. We also extract out all of these things: information retrieval, hardware, ergonomics, finance, transaction, document processing, medicine, and so on and so forth. So again, these are the axes that represent the vector space that the patents are embedded in. What we can do now with this innovation space and embedding is we can actually fuse patents and create, what would you get if you add a particular patent A and particular patent B? Can it actually create a new patent here? Right, so we've done that. We, take a patent A and patent B and then create a new patent, or we can actually generate abstract but we can also find the nearest neighbor. For example, if we take a patent for method and system for customizing view of information associated with social network user, and another patent related to healthcare, non-conformance monitoring and control technique for an implementable medical device, we get a new patent, or closest patent to this will be a concept to implement MedConnect, which is some combination of these two patents. Right? Another example, using multiple search engines to search multimedia data, you combine it with the system and method for rapid updating of credit information, you get process for protection against fraudulent use of smart cards and device for use of the process. Okay. You can also do more control generation. If you want to generate a patent with particular, more security, more portability, we can do that. All right, so I think due to the lack of time, I'm going to skip this part where we operationalize philosophy of creativity. And then what we did was we made some geometric interpretation, and we were able to come up with a different sort of a creativity level for patents. Then we correlated that to something like the 10-year for citation, which is representative of their scientific impact. We also did that with the dollar value of patents using what's called Kogan value. But let me just skip that. Another thing that we can do with this innovation space is we can characterize firms by their patents, right? So what we can do is this, in this latent space or the innovation space, we collect all patents owned by a firm, F, then obtain the average patent latent embedding as a centroid. Then we use the innovate decoder, right? We can do this, and what that lets us enable, or lets us do is we can actually, for each firms, create synthetic representation of patent abstracts. So basically, we combine all the patent owned by a particular firm, and then we let that representation generate an abstract. And that's sort of like a representative patent of the firm. We can sort of understand that. We did this for the big companies like Apple, Microsoft, Google, for Samsung. For example, Ford is a method for control the operation of a motor vehicle. You can see that the grammar is not perfect. The method includes the step of determining a current flow of motor vehicle, determining the current flow of motor vehicle. Samsung is a portable computer, so mobile stuff. Apple, a method for providing a user interface for a computer system, have a plurality of a computer system, and so on and so forth. So we can do this. Another thing, we can also find the nearest neighbor to a particular firm representation. So these are some top 3 nearest neighbor patents of these major firms. And we can also come up with what we call innovation index, which is a given patent X. Innovation index I is the absolute difference between posterior mean and prior mean at dimension I, or axis I, or technological factor I. So high index means that the patent is exceptional in this technological factor. Low index means the patent is average in this factor. We can also do this for all the interpretable technological factor that we have extracted. And we can actually rank companies. For example, in human-computer interaction, this is actually patent from 1980 to 2010. Nintendo ranked highest here, followed by Pixar and Immersion. For example, finance and transaction, Visa, followed by CME and Salesforce. Document processing, Fuji, NTT, and Dell, and so on and so forth. So I'm just like right now, just showing what we can do now that we have this entangle representation and vector space that we call innovation space. We can also visualize firms in this vector space. Again, this is just like 2-dimensional. In reality, this was a 30-dimensional. So you can see, you can compare and contrast different firms in different factors like document processing, human-computer interface, and so on and so forth. So I'm going to skip these and go into the conclusion. So considering our results within the context of econ of AI, we echo highly discussed path towards AI augmented invention to increase productivity. So Bloom et al. Has this paper that show that, evidence from various industry, product, and firms show that research effort is actually rising substantially while research productivity is declining sharply. So good example is in Moore's law. A number of researchers required to achieve the famous doubling of computer chip density is more than 18 times larger than the number required in the early 1970s. Right? So this is largely due to different effects, such as low-hanging fruit effect, things are already found. There's a burden of knowledge. Any one person cannot actually acquire all the knowledge to make this combinational creativity really easy. There's also curse of dimensionality. People have to specialize in a particular thing, and it's hard to connect in this sparse graph network, knowledge network, to make an invention. So thankfully, Econ of AI actually posits and argues that deep learning as GPT or general purpose technology and invention of method invention can perhaps improve performance in existing search-intensive research projects. So we have seen some examples in commercial and recent scientific articles. We have with this Innovate have shown and prototyped and shown that this is actually possible with patents as well. All right, so this is sort of a bit meta, but in 2019, there was a patent that was issued to these guys, and that basically automatically drafts patent given human provided claims. So claim is a bunch of things that determine, that distinguish patent and what's new about this patent. So once human gives that, this algorithm generates the entire patent automatically. So lastly, so I think I'm running out of time. So, I've shown you a prototype of generative model, disentangle representation learning, but generative models and disentangle representation learning in particular is still a nascent field that we're trying to figure out. It requires a lot of work still. It suffers from a lot of different problems like posterior collapse, measurement of disentanglement. Disentanglement is a problem in itself. Producing unrealistic instances or uninterpretable instances is a bit of a problem. But with much engineering and semi-brute force approach and actually injecting domain knowledge where we could, current algorithms should be able to provide a subset of useful concept of non-existing patents claims for humans to filter through. Right? So main takeaways, generative model can reveal insight about patents and innovation by situating them in an interpretable innovation space consisting of technological factors. And this approach enables more exploration at the firm level, the innovation factor level and patent level, and so on and so forth. Skipping this descriptive evidence. So this was more about showing the possibilities brought forth by the generative approach in business. So you can also sort of assume, imagine if you apply this same technology or approach to any other stuff that's in business, like products. You can situate product in feature space and then create new product. Actually, my colleague, Alex Burnup, is actually working on that too. You can also do this with the jobs, situate jobs in a skill space and do all kinds of inferences on the future of works. And that's it for me. Thank you for listening. I see a question. Have you applied this on prior art search and evaluating a patent submission? Art search. We haven't done anything with the art. We just patents. Yeah.
Okay. Hello, can you hear me?
Yep.
Great talk, Dokyun. There are a couple of questions in the chat. I'll read out the question in the chat. So you highlight the factors of dimensions of innovations embedding being interpretable. But how exactly do you even go about interpreting the latent dimensions automatically learned by variational autoencoders inside InnoVAE?
Yeah, great question. So this is still, there's always got to be a human interpretation there's no algorithm that tells you, oh, this is a factor and this is what we mean, right? So all of these things require human judgment, so to speak. What we do algorithmically is we actually, given a bunch of representation of a patent, we do a experiment, series of experiment where we just change the particular dimension and see what the difference is in the abstract that's being generated. And we can actually just collect terms that are highly changing or appearing. And that's how we sort of interpret what these factors mean. So basically jacking up, decreasing, increasing particular dimension and seeing the impacts. And then we collect them using, say, TF-IDF and things like that.
Okay, so Dokyun, I have a question. So, am I right in understanding that these disentangled dimensions of innovation are essentially the output of the encoder?
Sorry?
The disentangled dimensions of innovation are, by that, do you essentially mean the output of the encoder of the VAE?
Yes. Yeah, it's basically, yeah, precisely. So the latent dimension, the lower dimensional embedding that the encoder produces is what we mean. And then each dimension is rendered meaningful.
What do you mean by disentangled exactly? So this is not particularly clear. So how do you make the each coordinate of the output of the encoder disentangled? In what sense?
Yeah, so great question. I sort of skipped that part, but so disentangle, it just means that we add in a custom loss function, we add a term that basically pushes all the axes to the prior of that axis should be isotrophic multivariate Gaussian, meaning statistically they're meant a bit more orthogonal, but it doesn't guarantee it. But that's what we mean. So and also, there is actually an ICML best paper 2018 that shows that without particular inductive bias to guide this extraction of this entangle representation, you're going to have a hard time. So we apply inductive bias, by adding supervision of with the known structure data. We also have some Y variable to guide this entangle representation. But we had a bunch of inductive bias to do so. But it's more of it's both like engineering and art at this point. The field is ever developing. Yeah.
The loss function essentially ensures that the output of the encoder is an isotropic Gaussian. That's the goal of the loss function. I see. Okay.
Yeah, one part of it. Yes.
I see. So, there are classic methods like, for example, independent component analysis and so on, which kind of try to do that, but that's the main thing that they do. Is it related to those classic methods in some way?
Yeah. I mean, like there are a slew of methods, but they cannot handle multimodal, right? Like structured and text data all at the same time. You can't really do control generation in an easy way. Exploring this space is rendered a bit like it's ephemeral. As opposed to this approach, we're trying to figure out something that's a bit more interpretable and not permanent, but more sort of generalizable across all the data set points.
I have one other question regarding the way that how do you generate the representative patent for each firm, right? For example, you generated a representative synthetic patent for, let's say, Apple. Right? How would you go about doing that?
Yeah. So this is all in the latent innovation space. So we collect all the patents owned by, say, Apple, right? And we find the centroid, right? So basically, we find the centroid of these patents, and then we just put that representation into a decoder now. A decoder is trained such that it generates abstract. Of course, we can do it such that it generates a claims, it generates a summary, it generates a, whatever, right? So, but in this case, we just prototyped it with abstracts.
Okay, it's very interesting. Are there any other questions? No, it's the same question. Okay, so I think that's all the questions that we have right now, Dokyun. So if you have time, you can feel free to answer questions in the Q&A tab that opens up. But I think that's all we have right now. Thank you very much, Dokyun. This is a great talk. Thanks.
Thank you so much, everyone, for listening. It's an honor to be here. Thank you. Bye-bye.